Hey guys, this is the scientific investigation set of notes. It's the first notes that we're going to do. And because it is, I'm going to give you some advice just to start off. One thing you can do is speed videos up if you don't want to listen to me in real time and you want to make me talk a little quicker, which I actually do with videos too. You can click like 1.1, 1.2, 1.5, however quickly you want me to talk. There should be some kind of multiplier down towards the bottom of this video that you can do. The other thing is I am going to kind of go through the highlights. If you need to pause anything because you want to spend a little more time on a slide, by all means, go ahead and do that. But I am going to try to focus on the key takeaways that you might not otherwise get without me kind of pointing them out. All right. So with that said, I'm going to present, and we're going to start going right through this. Because this is all review, I'm not going to spend too much time here. You guys understand what the scientific investigation steps are. You've seen them before. The one thing I want to point out, and on the second slide it kind of highlights this, is that it's not always this nice linear progression of things. It's not always ask a question, then do research, then do your hypothesis in that order all the way down to the bottom without any changes, right? In real life, it's a little bit messier. So it looks kind of more like this, where you might have an issue and you have to go back to an earlier part of your experiment, and that can happen multiple times. So it's kind of like a circular thing where you're going around and around and you like redo things and then you go back through it and you recollect data and stuff like that. I just wanted to point that out, which is why this slide is here. All right, we're going to focus mostly on experimental investigations. That's where you're collecting data. It's probably what you're most familiar with. I just want you to be aware that not all science is about experimentation. Sometimes if you're like watching a nature documentary, you're observing animals interact with each other and you're observing their behavior and you're investigating it, but you're not actually manipulating anything. You're just a passive observer, right? That's descriptive investigations. Sometimes you don't even do your own independent study. You're just like analyzing other people's studies, which is actually a thing that you can do. That's called a meta-analysis. There are things like case studies where you only have like one thing you're looking at. Like clinical psychology often does that, where it's like based off one patient or something. So there's a wide variety of different ways to do science. Right? Let's go back to this kind of stepwise thing though, just to go through all the pieces. I think this is pretty self-explanatory. You make an observation or state a question. For this set of notes, I'm going to talk about the Pulse Lab and collecting heart rate data, because we're actually going to go ahead and do this in class. So maybe the problem here is that you want to know the effect of exercise on your pulse, right? That's your question. That's your problem. So that's what we're going to investigate. So let's make a hypothesis. Just based off of our kind of everyday experience with pulse, maybe we'll say, if we exercise, our pulse rate increases or whatever. If we exercise, maybe it stays the same in some instances. I don't know. That's what the experiment's about. So we're going to do some exercise and we're going to measure pulse. Typically, you'll use an if-then format. You do not have to use an if-then format. The only reason you are kind of told by your middle school teachers to use if-then is because it guarantees there are two things in your hypothesis that you need to talk about. The first is the independent variable. The independent variable comes after the word if. We'll talk about that in a second. The dependent variable comes after the word then. If you don't use if-then in your formatting of it, it's easy to forget to include either one or even both. So that's why you're usually told to just use if-then in your hypothesis. All right, so the IV, again, you guys know this. The IV is the thing that you change, in a pulse experiment, and we're looking at exercise. Exercise is what you're changing. You're either sitting, like I'm doing now, or maybe you're doing jumping jacks, right? So that is the thing that you're changing. The DV depends on it. It's your data, right? So we're doing pulse, so I sit here, I collect my pulse for a minute or whatever, right? and I get some data. And then I exercise, I do my jumping jacks, and I do the same thing. But the pulse, or my pulse rate, maybe beats per minute, in this case, is my dependent variable. It's what I am actually measuring. All right. Every time you do an experiment, you're going to have what are called levels of the independent variable. So in the pulse lab that we're going to do when we exercise, sitting is one level, and actively exercising, this is my motion for jumping jacks, is the other level. So there are two levels of the independent variable in this kind of pulse experiment that we're going to end up doing. Which one of those is the normal condition? Sitting, right? Sitting is the normal condition, or kind of standing or not moving. Usually you're not exercising as the default. So if you, and you don't always have to have a control, by the way. Not all experiments have a control. Just be aware of it. But oftentimes you will. The control is the normal group, whatever's the normal situation, and it's the comparison group. People get controls and constants confused all the time. You will too. So I want you guys to pay attention to this. Constants are things in your experiment that stay the same. Right? The time of day you do the activity, the length of time you take your pulse for, the type of activity you're doing. If you're doing jumping jacks in one trial, you're not going to do squats in another trial. You're going to keep that activity the same. Typically, you want 10 or more constants per experiment. And it'll take some creativity and brainstorming to generate a list of constants. Repeated trials, you guys know what these things are. You know why they're used. 3 is the absolute bare minimum. You want as many as you can. The only reason we don't have an infinite number of repeated trials in an experiment is because it just takes time, energy, and perhaps money to do. So there's usually an upper limit, but you always want repeated trials so that you can calculate averages and so that you can eliminate outliers. All right, quantitative versus qualitative data, I think that's pretty self-explanatory. Observations versus inferences, again, pretty self-explanatory. I'm going to skip that. Analyzing data, you will be probably not graphing too much because you're just not in class with paper, you're doing it virtually. I would recommend getting used to some kind of graphing tool, maybe like Excel if you're a Microsoft person, and then I think Google has their own version of that if you are a Google person. But the IV goes on the x-axis, the DV goes on the y-axis, right? This is stuff that you guys know. Make sure you have your labels, make sure you have your units, make sure things are titled, right? So this is all review anyway. We'll work on it this year too. All right, your conclusion is usually a paragraph. You guys, again, you know how to do this. You're going to start with your purpose. Why are you doing the experiment? And you're just going to walk me through all the parts, your hypothesis, what your results were, and what you can conclude, right? Don't be afraid to tell me that your data does not support your hypothesis. That's usually the case, and that's perfectly fine. I would rather you be honest and admit that your data just didn't support it than try to fudge the data or lie about your hypothesis, right? If your data doesn't support it, tell me. You will never be wrong if that's the case. You'll never lose points or anything like that. Honesty is paramount here. Especially kind of in our current environment where it's getting a little bit difficult to figure out what's scientifically accurate or not. If you are lucky, again, most things are not published, but if you go through a rigorous peer review process where maybe other physicists or other biologists or other chemists look at your study and approve it, you can get it published in a scientific journal. And that's why we like to have you guys go to these journals when you do research, because they are vetted, they've been reviewed, and they're very reliable compared to something like BuzzFeed or just a run-of-the-mill Google search, which is not peer-reviewed. So it's the peer review process that makes scientific journals so much more robust and reliable when you look up data. All right, so that's it for this. Again, I'm going to try to keep these videos under 20 minutes. I will discuss these with you guys the following class. So if you have any questions at any point in any content lecture or PowerPoint, there will always be an opportunity to discuss this together the following class day. So I will see you guys tomorrow.